All right, so we have started recording. So as I was saying, on Monday's class, we were discussing the stress-strain relations or the stress-strain diagram. Specifically, we were talking about the engineering stress versus the engineering strain diagram. And then I introduced to you the idea of the true stress, true strain. Now, in the very same plot or in the very same figure that we discussed the engineering stress versus the engineering strain, it is possible for us to plot out the true stress versus the true strain diagram. So let me start sharing the screen. Please let me know if you can see this thing. Can you see my shared screen?
Not yet.
No, sir.
No?
No, sir.
No, sir.
No, sir.
Now?
Yes.
Yes.
Sir.
All
Yes,
right,
sir.
all right. So let me actually move over to the workspace where my writing app is, and you please confirm if you can see this green colored writing app.
Yes,
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
So I'm continuing on the same set of slides that we were discussing on Monday, and I'll continue from there. So you see, we had this diagram, and I had made a mess of it by explaining, but it's good. We want it to be like this. So I'll read out this diagram very quickly. Let me just, what I'll do is I'll just do this thing in this yellow colored plot, okay? And I'll not do any labeling. So, okay. So please don't mind the bad diagram.
Sir?
Yes.
Sir, I heard out in means shear strain. Like we define gamma as means a deflection of infinitesimal lines segments which are perpendicular to each other, like that is theta 1 plus theta. Sir,
Right.
so we cannot define means some other strain in 3D, like which have three such lines which are perpendicular to each other, and the deflection theta 1 plus theta 2 plus theta 3 from the axis.
So you want to come up with a new definition of strain?
Yes, sir. Sir, which represents the overall strain of a body.
So there are certain issues with it, okay? So what you can do is maybe you can just post this question in the channel, the chapter 0 channel that I have started. You post this question there and I'll try to answer it there. Okay. So since we have this last precious 1 hour to finish up this discussion regarding the true stress, true strain, and a bunch of other things that I have planned for, let us not invest the time to answer this question which you have suggested. It's a very good question, no doubt, but it's a bit outside the scope of what we are supposed to discuss officially. Okay. Nevertheless, I will try to answer it, but maybe after the class is over. Okay. So right now you listen to what we are discussing, and after the class is over, you post the question in the discussion channel. I'll try to answer it there. All right. All right, so this is our engineering stress versus the engineering strain diagram. I've just repeated what I have drawn in the previous class. Please note that this is not like something which is true or correct for any kind of material. Certainly not. So if you are if someone comes along and asks you to draw the engineering stress versus the engineering strain diagram, you have to first ask that person for what material. If he or she says that draw it for low carbon steel, then draw this diagram. Otherwise, don't draw this. For example, and we will discuss this, the engineering stress versus the engineering strain diagram for something like aluminium is completely different from this. Okay, it has some commonalities, but overall it's quite different from it. So let me just write this down properly here, that this is for low carbon steel. The reason why this particular diagram is very, very popular and common, and you will find it invariably in any textbook of mechanics of materials, mechanics of solids, is that this low carbon steel, it's a very popular material. It's a very widely and commonly used material. Many of the day-to-day structures, they're made of this low carbon steel. However, this low carbon steel, its strength is not very high. So the strength is represented by this point. Okay, by this point here, the topmost point, that is the ultimate stress. Now, we were going to discuss about the true stress, true strain diagram for the very same material, low carbon steel. What does that look like? Well, let me first draw it, and then I'll try to bring to your attention certain things. So up to this point, okay, up to this point, okay, it is the same. We go up like this, more or less the same kind of things that you see for the engineering stress, engineering strain diagram. It's the same thing. Now, after it has reached this point where the strain hardening phenomenon starts, you will see that the plot for the true stress, true strain diagram, that goes like that. Okay, so maybe a little bit less. So let me draw it with a slightly lesser slope, otherwise I'll be in trouble later on. Okay, something like that. Please note that both of these are the stress strain diagrams. Both of them are obtained from a tensile test. So from the very same experiment that you carry out, you can obtain two plots. One is the engineering stress, engineering strain diagram, the lower one, and the upper one is the true stress, true strain diagram. Okay, so let me just write it here. This is the engineering one, and this is the true one. Okay. Now, all this was for tension. Okay, for the tensile test. Now, question is it ever possible to draw something corresponding to this for a compressive test? And if so, is there going to be any difference? Answer is yes and yes. Okay, it is very much possible to carry out compression tests. People do it all the time. And it is also possible to draw a plot like this, and you will find certain differences. Okay, so what is that? So first of all, what we'll do is we'll try to draw the engineering stress, engineering strain diagram for a compression test. Okay, and for this I will change the color, otherwise it will all be a confusing mess. So let me use the orange color. Now you tell me one thing. Okay, if I want to draw the compressive stress versus the compressive strain diagram, do you think that the plot will be drawn here in this quadrant, or should it be in some other quadrant of this sigma axis or the epsilon axis? So this entire plane, we have this is the first quadrant, right? For the compressive one, where should we draw it?
The second quadrant.
Second quadrant.
The second quadrant.
The second quadrant.
And third.
So somebody is saying third. Third is actually the correct answer. because in the third quadrant, okay, in the third quadrant, when you go here, in this quadrant, both sigma and epsilon, they are less than 0. So this is the correct depiction or representation of the compressive regime. So you understand that when you are doing compression of a very slender bar, then the length is decreasing. Since the length is decreasing, the algebraic sign of the epsilon value, that is less than 0. I mean, that is minus. Similarly, the sigma, because it is a compressive kind of force which is giving rise to this compressive stress, that is why the algebraic sign of this sigma is also negative. Now, we should ideally be drawing this plot in the third quadrant. However, we want to have a way of directly comparing with what we obtained in the tensile test. So our tensile test was in the first quadrant. We want to have a direct comparison with it. And for that, it is the comparison of the magnitude. So what we'll do is, we will take the magnitudes of the compressive stress and the magnitude of the compressive strain and draw those magnitudes in this first quadrant. All right, so let me do that. So it's like this. When you are trying to draw at least for low carbon steel, when you plot out the things, it is more or less like this only. Okay, it is more or less like this. I mean, there may be some differences in this very small zone where you have the yielding just occurring, but at least up to the strain hardening part for low carbon steel, there is practically no difference in the magnitudes of the compressive stress and the tensile stress. But after this thing, there are differences. So this is where we obtain a plot like this. Okay, so this orange colored thing, this is the engineering stress versus engineering strain, but for the compressive case. So I will write C within the bracket to represent compression. Here I will write T within the bracket to represent tension. Now we are following the same idea as before. First, we are drawing the engineering stress versus engineering strain. Next, we want to draw the true stress versus the true strain. And this one I will not draw. Rather, I will ask you where I should draw the thing. I will tell you one information that again, if I let me come to the question. So again, up to the strain hardening part, it is going to look like this, look the same. Okay, there is practically no difference between the true stress, true strain diagram and the engineering stress, engineering strain diagram for the compressive case, just like as it was in the case of the tensile case. But after the strain hardening sets in, there is a difference between the true stress, true strain diagram and the engineering stress, engineering strain diagram, even for the compression test. Question is, where should it lie? So someone was saying below. So below what?
Sir, below engineering compression.
Engineering compression.
Okay, below this orange colored thing, right?
Yes.
Yes, sir.
Okay. Now, next question is, below means this is also below, this is also below, this is also below. Which one?
Sir, above the yellow, true.
Right, right. So it's like this, that for most of the region, for almost the entire region, it is very, very similar to the true stress, true strain diagram for the tensile case. But then as the values go higher and higher, there's a slight difference, very, very slight difference. I'm exaggerating here, okay? So it's like this. something like that. Okay, and this is the true stress, true strain diagram for the compressive case. Now you tell me, first of all, that why there is this difference between the true stress, true strain diagram and the engineering stress, engineering strain diagram for the tensile case.
Sir, because here the area will increase, not decrease.
No, no, for
That's
the
why it will
tensile,
come.
for the tensile case. For the tensile case, I'm asking.
Sir, the stress will increase, so subsequently, so the strain will also increase proportionately along with the stress. So it is a little bit above the engineering stress state diagram in the tension case.
So see, whether it is the tension case or the compression case, you have to understand very, very concretely that the loading which is applied. So in the actual experiment that is done, some kind of loading is applied. Some kind of weights are actually placed. So the value of these weights are the same. Okay, in fact, the entire experiment is the same. It's just the data points that are generated for the true stress, true strain diagram versus the engineering stress, engineering strain diagram. They are different. So the only difference, it lies in the consideration of the area. So for the engineering stress, engineering strain diagram, in the tensile case, you have a certain area, and that area is the original area, the undeformed area. Even though in reality the area is decreasing, so you will have the slender specimen which was initially like this. After deformation, it elongates, and slowly in the middle region it becomes thinner. Okay, in the middle region it becomes thinner. So what actually happens is that the area is decreasing. So you have the same force. Okay, so sigma is like F by A. You have the same force, but this current area is decreasing. Okay, so when you have the sigma true stress, this is the current area, and the sigma engineering stress, you have the same force in the numerator, but the area is larger because it is the original area. So naturally you have this sigma T value greater than sigma E. Okay, so since your A is less than A naught, therefore sigma T is greater than sigma E. That's all there is to it. Now you
Hello, sir.
tell me, yes.
So at the breaking point, why are not the strain same for the tension and compression cases? Means,
Because
sir,
the
in
because it's, you see, I have written this as a common epsilon, but actually it is the true stress versus true strain diagram. This is the engineering stress, engineering strain diagram. So the value of the strain calculated is also slightly different. If you look at the previous page, where did it go? You see, this is our formula for the true strain. So epsilon bar was given like natural logarithm of LF by L naught. But the epsilon that was calculated with respect to the, like, directly L minus L naught divided by L naught. Okay, so there is a certain difference.
okay,
My next question is that you see here the compressive stress strain diagram. If we consider the engineering one versus the engineering one, this compressive case is much higher than this tensile case. I mean, the difference here is slightly exaggerated for clarity, but it is higher. It is definitely higher. Why is that? Why do you think it is?
Sir, while compressing, the area will increase a little bit. So
No, no, no,
like
no. We
this.
are comparing engineering versus engineering. Here in the denominator, only the A naught is there. So that has nothing to do with the area. I'm
sir,
saying,
because the material can handle compression better than tension.
why better? That is the question.
Sir, because like the intermolecular forces while tension, so like we are trying to separate the molecules. So, but the intermolecular forces and compression, we are pushing the bar from both the sides. So we are actually supporting the intermolecular forces. So I think that's the reason why the material can handle compression better.
Your thinking is somewhat correct, but there is a slightly more sophisticated way you have to think about it. You see, actually, in terms of the intermolecular strengths, when you are trying to compress it and compress it quite heavily, because you see, the compression as far as you are concerned here, in this region, that is not too much. But when you go into these regions, the higher compression regimes, it is there that the differences arise with this tension case. Now, if you really are pressing hard against the material, you are trying to bring the atoms or molecules much closer than they are supposed to be in accordance with their chemical bond lengths. Okay. Now, beyond a certain distance, if you want to bring two molecules closer together, there are extremely high repulsive forces. The repulsive forces are actually very, very high. Okay, so that is one of the reasons, but that is from a very, very, atomistic perspective. Even without going into that, let me just finish. Okay, even without going into that atomistic perspective, there is a way of thinking about it from a very macroscopic viewpoint, from a very mechanical macroscopic viewpoint. You see, this kind of a specimen, when you are pulling it or pushing it, this kind of a specimen is a real specimen. All right. It is not that we are carrying out a thought experiment. It's a real physical hard experiment. Now, this slender rod, it is going to have some kind of microscopic defects or very small scale defects. Maybe there are some very small cracks present or some imperfections present, some material inhomogeneities present. Now, when you are pulling against the two ends, pulling at the two ends, and if those micro cracks are present, there is a chance of those cracks enlarging. Okay, so you are not actually helping its cause to maintain its structural integrity by pulling against the crack. So suppose you think that you have a sheet of paper in which there is a slight perforation in the middle, and then you are pulling at the two edges of the paper. So, that paper will barely be able to sustain your tensile forces, your pulling forces. It will just tear apart. On the other hand, if you try to push against the two edges of the paper, now for a paper, it doesn't make too much sense to talk about compressive thing because it doesn't support compression very well overall. But suppose you have a thicker piece of paper like a cardboard piece or something, and then you have a perforation in the middle, and then you are trying to push against the edges, it will be able to maintain its structural integrity, or in other words, it will be able to not tear under the action of those compressive things. So it can sustain higher forces and consequently higher stresses. That is also one of the reasons. So the two reasons that we have discussed, they are not exclusive in nature. They work together hand in hand along with a number of other microscopic reasons. So as a result, the stresses that appear for this compressive diagram, they are much larger than this tensile. Okay, somebody was saying something.
Yes, sir. So actually, I was thinking that suppose if we see one section with one cross section of that slender bar,
Right.
then if we try to pull it, then area is decreasing. It means if we see the items in that cross section, then means they are going to come closer, so there will be more repulsion in that case.
So you're saying that this suppose we consider this small region here when they're coming closer to each other.
Yes, sir.
Yeah, but it's the thing that the material points which are present here, they are not just coming close to each other. They are, some of them are also moving up and down. Okay, is
Yes.
as opposed to that. So you are thinking about the tensile case. In the compressive case, there is barely any place for it to move out.
Yes, sir, I got it.
All right. There's a subtle difference between the two. Okay, but I'm glad that you brought this point up. Okay, now the question is, I mean, this is the
Sir?
easiest question. Yes.
Sir, why
Yes.
there is a difference in true tensile and compressive one? The slight difference is there. What causes it?
Reason is the same reason. Okay, so the true
There's a force of attraction.
true stress, true strain diagram for compression is slightly higher than the true stress, true strain diagram for tension for exactly the same reasons that we were discussing. All those microscopic reasons when you are pulling it versus while you are pushing. But since there is a better accounting, since there is a better accounting of the actual area under consideration, that is why the differences don't show up in such a massive fashion as opposed to this engineering stress case. As opposed to this, yes, engineering stress for the compression versus the tension. Yes, somebody else was saying something.
So we can measure ultimate stress point only via engineering stress strain plotted by tensile test, right? Can it be measured in any other way? Like in the other cases, the graph is only increasing; it's not falling down any.
Yes, you're absolutely right. The ultimate stress thing that is actually defined with respect to this engineering stress, engineering strain diagram corresponding to a tensile test case. Because here for the true, first of all, for the true stress, true strain, it is just keeping on increasing like this. So what is ultimate stress? Ultimate stress is basically where it is just, if you had to define something like ultimate stress, and it's certainly not called ultimate stress, it would be equal to that, the value that it is where it is rupturing. Okay, similarly for this case. Okay, so this ultimate stress thing, the maximum value that the stress is obtaining, that is only relevant for this engineering stress, engineering strain diagram corresponding to the tensile case. Okay, so let me speed things up a little bit and just ask you one last question here, that this engineering stress for compression is larger than this true stress for compression. What's the reason?
The area increases here.
Right. So here is just the opposite case to what it was for the tensile one. So here for the compression one, A is larger than A naught. Okay, so this is for tensile. Okay, this was for tensile. For the compression, A is larger than A naught, so sigma true is less than sigma E. All right. Now, remember, I'm again emphasizing this is for low carbon steel. Now, it is very much possible to have these kinds of stress strain diagrams for other kinds of materials. And it is also very, very important for me to highlight that this material, this low carbon steel, this is a ductile material. Okay, so without going into the formal definitions of ductile material, you know that ductile materials are materials where you can elongate them very significantly. You can draw them out into wires. You have learned these even in your school. Now, of course, there are formal definitions for ductility and all these things. We are not going to go into that right now. So what we want to do next is consider another kind of ductile material, which is very common, which is an aluminium alloy. Okay, there's a bunch of aluminium alloys which are actually used in various day-to-day structural purposes also. Sometimes you'll find them used in in things like these modern window frames. You'll also find at least some variety of them in some kind of very small supports. Okay, maybe for some kind of wall hangings or some kind of small appliances. So they are used as small bars from their jutting out from the walls, and they're used as some kind of supporting platforms. So these are very small things which can be used with aluminium. Now, what is the diagram for this? Okay, so diagram for this, let me draw it in a fresh page again. What I'll draw is, first let me draw this low carbon steel again, so you'll have some basis of comparison. This is for the low carbon steel. Somebody has unmuted themselves. Please, can you mute yourself? There's some background noise. All right. Next, let me use this, let's say, separate color. Let's say this green color. Now I'm going to draw for aluminium. So it's something like this. So take a look at it, consider it carefully for a moment, and then try to draw some conclusions from it. Okay, maybe this is not the best of diagrams. Something like that. So first of all, you see the slope of this stress strain diagram for aluminium. Let's put this. This is some kind of an aluminium alloy. The slope of this stress strain diagram is smaller than the slope of this stress strain diagram for low carbon steel. What is the implication of this? Who can tell me? So when the strains are very small, the slope is this is a linear region. Okay, this is very much straight. Like this yellow color thing was very. What is the implication of that lower slope?
So there will be more strain for less stress.
No. In terms of material properties, you know this. That's why I'm asking. Very good. Very good. Yes. So Young's modulus. Okay. So Young's modulus of aluminium alloy is less than the Young's modulus of this steel. And if you go back to all your tutorial sheets from your first year, you will see it was mentioned to be something around 200 and 200 GPa. Okay, so something like 200 GPa, gigapascals. And aluminium, wherever it was mentioned, and you have done a bunch of problems associated with it, it was something like 70 GPa. Okay, there is a significant difference between the two. However, you see the ultimate stress for aluminium and the ultimate stress for the low carbon steel, they are more or less the same. Okay, so that's a nice thing. However, the value of the strain at which it ruptures for aluminium, that is much lower than the value of the strain at which the low carbon steel material ruptures. Okay, so there is a one similarity and a couple of differences. Okay, but you tell me there is one major difference which is like present right before our eyes, but I have not mentioned it. Can you see the difference?
There is no plateau region.
Plateau region is not there.
Yes, very good, very good. That is the thing. There is no plateau region. In fact, you see for the low carbon steel, there is a very distinct yield point. So this little point where it is pointed, okay, like a mountain peak. Here, this point, it is referred to as the upper yield point. This is like the lower yield point, but of course, this diagram has been sanitized a lot. Sanitized means I mean, we have cleaned it up a lot from the actual way that it looks from actual experimental data, but more or less this is the overall thing. So we have a clear-cut yield value for low carbon steel. As opposed to that, for the aluminum alloy material, there is no clear-cut yield value. Like where this linear region is ending and where the strain hardening region is beginning, we are not quite sure. Okay, and that has some implications in the way that the design considerations have to be, or the design decisions have to be made. Okay, and we will come to that in a few minutes. But before I go on to that, you please note that both this aluminum alloy and the low carbon steel, they are ductile materials. Okay, so this is again ductile. Very much. This also, of course, is ductile.
Sir?
So everything that we have been discussing has been pertaining to ductile materials. Yes.
Sir, how do we define the plastic limit for aluminum alloy, like till where it can regain its shape?
I told you, now I'll come to that in a few minutes. Just give me a moment. First, I want to finish up another bit of discussion. So, see, we have been discussing about ductile materials. Now, there are a bunch of materials, very structural materials also, day-to-day materials, which are not ductile, which opposed to this is brittle. Okay, so what is the hallmark of a brittle material? What is the main principal feature of a brittle material? Who can tell me?
Sir, it breaks as a flat surface.
Okay, breaks as a flat surface. That you will learn certainly in your experimental things, but in terms of the deformations.
So the strain at fracture point will be very less.
Right, that is the correct thing. So a ductile material, even by your high school definitions, it is something which can be drawn out into long wires. So drawn out into long wires in terms of deformation basically means that it can undergo very large deformations even without breaking. And you can actually see that. So these values of strains, these are, I mean, quite significant. Okay, the value at which it ruptures finally is quite a significant. It has a long journey here. As opposed to this, a brittle material, it'll keep on deforming a little bit, but then suddenly it'll just break apart. You cannot draw out a brittle material, for example, chalk. Okay, like the chalk pieces that we write on our blackboards, that you cannot pull out into a thin wire. Okay, similarly, glass. Glass is a brittle material. Cast iron, that is a brittle material. You cannot draw out a cast iron into a thin wire. Okay, so on the stress strain diagram, I want to draw that thing again. So let's draw it for cast iron, which is a very common engineering material. And let me use a different color for this. The cast iron stress strain diagram will look something like this. Okay, barely it starts to curve like this, and then it just breaks apart suddenly. So this is for cast iron. And this is a very brittle material. And you will have the same sort of behavior, well, not exactly the same, but at least in terms of how much deformation it can sustain. It's the same kind of behavior for glass, for concrete, for stone, things like that. Okay, you also note that the value of the Young's modulus for this cast iron will be lower than even aluminium. All right. And as someone was mentioning, when it ruptures, when it breaks apart, these brittle materials, they look like this. So suppose you have this kind of a brittle material, again the same kind of slender rod, you start pulling at the two ends, it will deform a little bit, it will elongate just a little bit, denoted by this small value of the deformation, and then when it breaks like this. Okay, so this is brittle. As opposed to this, for the low carbon steel, when it breaks, it will look like this. something like that. These are highly exaggerated diagrams, of course, just to give you a clear picture. But you see, there's a pointed region and there is a hollowed out region. So this is referred to as a cup and cone kind of fracture. Okay, cup and cone kind of this thing, and this is like a flat thing. Now, this is not something like a history lesson or a geography lesson. There is a very sophisticated reason behind why this is happening. However, I will not discuss it right now. Okay, later on when we come to the chapter on transformation of stresses, we will discuss this again. Okay, if I forget to discuss this, you remind me. Okay, but I will not forget. It's a very important thing. Yeah, somebody is saying something.
Are these diagrams irrespective of initial dimension of this material?
Please say that again.
Sir, the diagrams shown there are irrespective of initial dimension of material.
Very good question. Very good question. Thank you. So yes, so these diagrams you see, they are for stress versus the strain. All right. And the reason that we plot these diagrams for stress versus strain and not force versus length is that very same reason. That when you draw something for the stress versus strain, it is independent of the initial dimensions of the material. Okay, it is independent of the initial dimensions of the material, because you see this epsilon value, it's a relative change in length. It is not the actual elongation. It's not the absolute value of the elongation. It is rather the relative value of the elongation, whether it is the true strain one or it is the engineering strain one. It is a relative elongation. Okay, that relative elongation may be calculated in different ways, but it is after all a relative elongation. So it is kind of like a normalized value. Okay, it is like a normalized value, and you can almost think of it in terms of the absolute grading or the relative grading that you get in different courses. So suppose in a course, the highest person gets 60 out of 100, and the second highest person gets maybe 50 out of 100. So it is not that bad. It doesn't look that bad in a normalized fashion. Okay, so the initial dimensions of the material, that has absolutely no influence in how these plots look like. As opposed to this, if you were to plot the force versus the length diagram, then these diagrams will look completely different for different kinds or the different dimensions of the initial specimens that you deal with. Okay, so very nice question. Okay. As I had told you earlier, so let us consider this aluminium thing and talk a little bit about the way the yield value is calculated. Because you see, experimentally, there is no clear-cut yield value. All right, so let me draw this thing again. Something like that. This is aluminium alloy. All right. So as far as the slope is concerned in this linear regime, up to this proportional limit or whatever, so this the value of this Young's modulus, finding it out is not a big deal. Okay, you find out the slope of this line, that's your Young's modulus. But what about the yield value? Whether it is here or whether it is here or whether it is here, which one? There is no clear-cut indication from the experimental data. So when there is no such experimental indication, what we do is we agree upon, like we engineers, we agree upon some kind of common like a criterion for yielding, and that common criteria for yielding is given by something called the offset. Okay, so this is referred to as the offset method. Offset means compared to this origin, how much right hand side I will go. So let's say I choose this point, and this point is chosen, and in a fashion, well, where it is said something like it's a 0.2% strain. Okay, 0.2% strain means, okay, so offset, if it is said something like 0.2% strain, it means it is equivalent to a value. It is equivalent to a value of 0.002. Okay, 0.2% means 0.2 divided by 100. Fine. Similarly, you can have a 0.4% offset also. So in that case, it will be 0.004. Okay, so once we decide something for a particular material, we'll have to stick to it. Now, what we do is, from this point, we draw a line which is parallel to this line, which is parallel to this line, like this. And where it meets the stress strain diagram, from there we mark out the value. Okay, so this value that we refer to as the yield value of aluminium alloy, considering, so if we say that this is 0.2%, if we say that this is 0.002, then it is corresponding to a value of 0.2% offset. As opposed to this, suppose it was said that we are going to choose a 0.4% offset, then the value would have been like here, and it would have been a slightly higher value of the sigma yield. Okay, so sigma y subscript means sigma yield. Okay, so this y, okay, this y is the yield value. That's it. That's all there is to it. So do you have any question on this?
So here we are.
Sir, I have a question.
Somebody was saying before. Please say.
Sir,
so here we
I
are
have
assuming the strain. Okay, I'm sorry. Please go ahead.
No, please tell.
Okay. So here we are kind of assuming that like we are setting an offset, and then whatever the value comes up, that we are taking it as yield strength. What if it is what if the assumed yield strength is higher than the actual yield strength, and I go to an extent
There
and
is no,
it kind of
I understand.
It becomes plastic. Yeah.
Yeah, so I understand your question. So suppose we don't know anything about the material in hand, and just arbitrarily we say that, okay, my wish is that I will take an offset value of 0.01% offset. My wish, right? So just like I have said 0.2% offset or 0.4% offset. Suppose I claim that I want to take 0.01%. Okay, now that kind of a low value, just because we say something, it may not be too compatible with the actual experimental data, which is why these kinds of things are not arbitrary. Okay, so only after sufficient number of experiments have been done and people are absolutely sure that there is a certain observable deviation from this linear behavior, and that they take this kind of a value, so that when you draw this kind of a parallel thing, you will actually end up in this non-linear region. Okay, so things are not just arbitrary. Even like you cannot choose an offset value without first having done sufficient number of experiments and getting some experience with the material. All right. Yes, there was another question which was going on almost simultaneously.
Sir, I have some doubt that in low carbon steel, the engineering strain and true strain stress curve for the compression, it will be a negative. So why should we have not drawn in the third quadrant?
I told you, now we are drawing this the magnitudes. Okay.
Okay, sir.
Yeah, both of them are magnitudes.
Okay, sir.
Sir, I have a question.
Yes.
So why did we create one more term called offset to find the yield point? We can directly find the yield point by using. We are already performing the experiment to find the yield, to find the offset, right?
I did not understand your question. Say that again, please.
So as you said now, we fix a particular value of offset by doing some experiments.
No. First, we draw the stress strain diagram. We look at it carefully, and then after we have gained some experience, we choose a particular value of the offset in such a way that we are surely and safely within this nonlinear region. Nonlinear means, you see, this is the linear region, no, where there is a linear relationship between the sigma and the epsilon. However, beyond this point, let's say, there is a nonlinear behavior. So if you want to plot or you want to write a formula for the sigma versus epsilon, it will look like something like sigma is equal to k times epsilon to the power n, where n is not equal to 1 in this region. So you take the value of the offset by observing, not by carrying out an experiment. Okay, this offset choice is your choice. Your choice means like proper engineer's choice, such that the point that you end up here lies safely in the nonlinear regime, in the strain hardening regime rather.
Yes, I got it.
Okay.
Sir, like in the low carbon steel diagram, we had a point where we applied a stress. So from that point, it tend to return to the original, like the original length. So that's called the plastic limit. So
Right.
Till that point, the slope was constant. The slope of the graph was constant. So
Yes.
why can't in the aluminium graph we can
Yes.
say that till where the slope is constant, we can take it as the the plastic limit for
Very
the
good.
stress.
I understand what you're trying to say here. So you see, these kinds of diagrams, they are drawn. I have drawn it like a continuous thing, but you understand that when you do an actual experiment, you don't get a smooth plot like this. Rather, you get a scatter of points. Okay, so in reality, what you obtain is get a point here, you get a point here, maybe you'll get a point here, maybe you'll get a point here, you get a point like that, like that, like that, like that. Okay, so unless you carry out like a very high number of experiments, extremely high number of experiments, you are sure to miss out this actual point where it is yielding. Okay, the kind of fine-grained thing that you are trying to say, in order to do it experimentally, it's not so easy. That is why what people do is they carry out these experiments, they obtain the graph, and then in order to be absolutely sure that the kind of value that they obtain for the yield stress of aluminium, it's a commonly obtained value. They take this offset method. Otherwise, by the method that you are suggesting, that is certainly true to the physical truth, but because we are limited by the sensitivity of our experiments and the number of experiments that you can carry out in different places, so there is a high chance that there will be significant difference in the values of the sigma yield that will be obtained by one set of experimentalists compared to another set of experimentalists. And please note that these are things which are a little bit sensitive to the ambient temperature also. So there is that extra degree of extra degree of control which you need to exert. I mean, an experiment carried out in Paris and an experiment carried out in Kharagpur may actually yield different values of the yield stress just because you have not accounted for the difference in temperature. Okay, however, if you are choosing this kind of a offset method, sure, you are losing some sort of fidelity with or faithfulness with the physical reality, but there is a lesser chance of getting widely different values of these yield values, of these yield stresses. I hope I have made my things myself clear.
Yes, sir. Yes.
It's not like a computer generated plot, right? That, I mean, it's just a matter of changing the increment values of a for loop by from 0.01 to 0.005, and then you get a better, smoother plot, and then you can just find out the thing. Really, it's an actual experiment. Okay, so these are discrete data points which have to be generated hard from the table. So there is like a big likelihood that this region, okay, you may miss the actual yield point. But very nice question. These are the kind of things which I want you to think about and like question. All right.
Sir.
So see, officially class is over. Okay, officially class is over because time is over. You're all free to leave and go to your next class. I think your next class is dynamics, but if someone wants to hang back and ask a couple of questions, it's fine by me. All right, so class is officially over. You can all leave. Yes, somebody's asking something.
So one small doubt, sir.
Yeah.
So can we use strain gauges to get continuous like plot and all? So we can use this derivative and
you can use strain gauges to obtain the values of strains at a particular point. But here we are not talking about that kind of strain. We are talking about the strain considering the entire gauge length. Gauge length means when you take this kind of a cylinder, you mark out 2 points on it, relative to which all changes in length are calculated. Okay, so this is the gauge length. That is like your L naught. And as this thing is pulled apart, this point moves here, this point moves here, and then it moves here, and then it moves here, and you keep on changing the differences in lengths. Okay, so when you use strain gauge, you stick the strain gauge at a certain point like this, and then at that point you can find out the values of the strains in different directions. You will not be able to find out the changes in the gauge length using strain gauge. All right.
So like, why do we require the length? Actually, we are plotting the stress versus strain graph, isn't it? So only strain value is enough.
No. So this here we are not actually calculating the strain at a particular point. We are actually calculating the relative changes in length. Okay, which of course will have some correspondence. So for example, what you are probably saying is that why not stick a bunch of strain gauges along this? So maybe we put a strain gauge here, we put a strain gauge here, put a strain gauge here, calculate all the values of the strain gauges or the values of the strains in this direction, average out from these various strain gauges, and then maybe we get a maybe more accurate picture. Something like that you are probably saying, right?
Yes, so that's better.
Yeah, that can be done, I think, in theory, but then there is something called an experimental protocol. Okay, so the tensile testing thing has been done for so long that whether you do it in India or in France or in the UK or the US, there is a certain protocol people follow, and as long as you stick to it, people can agree upon a commonly accepted thing. Like one can, of course, set out different sorts of protocol or experimental protocol. And why just strain gauges? Strain gauges are quite old. You have very sophisticated optical instruments to find out deformations even at the micro scale. So it is very much possible to obtain more sensitive values of these things using such digital sensors. But then if you do that, you have to ensure that the values that you are comparing against in different places, that has to be by the exact same protocol. There is no problem as such. Scientifically, there is no problem. It can be done. Okay, but when you say that I am drawing the engineering stress, engineering strain diagram, it is usually understood that you are using a standard tensile testing equipment where this is the experimental protocol followed. So every engineer can understand what is the background behind this data.
Sir, I have a doubt.
Yes.
So initially we started our discussion by assuming stress and strain at a point, and now we are plotting the graph for a slender rod or so. So
Yes.
I'm unable to link both the concepts. So
you're absolutely right. So this epsilon value that you are saying, that we are saying, this is more like the kind of thing that which you studied in your high school. Okay, so and just now the question that we had regarding the strain gauge, the calculation of the value of the strain using a strain gauge would be more in keeping with the formal definition of the strain, because strain is actually theoretically defined at a point. But when you are writing this strain, it is more like we are saying it as a relative change in elongation, considering actual non-infinitesimal lengths. Okay, but this is the kind of, as I said, this is the kind of protocol people follow. Like now it has been more than 100 years that people have been following this protocol to find out the values of these kinds of engineering materials. Okay, of course, if you have to go for some kind of newer materials which have far more sensitivity, which are far more difficult to carry out experiments using this tensile testing, then you will have to go for new and innovative methods of doing these things. In which case it is possible that the theoretical formal definitions of strains which you have defined, that will be respected more compared to these old methods. Okay, which is not to say that these old methods are wrong, because you understand that no matter how sophisticated a theory you provide or a formal definition of something you provide, the ultimate test of engineering lies in the stability and the integrity of the structures that you build. Okay, and you have to respect and admit the fact that even if these methods are old, even if the values of the Young's modulus that have been calculated using these methods are rather old, and this is not directly respecting the formal definition of the strain at a point that we are saying, even with all those like apparent defects, the structures which people have made based on these values, they are still standing, they're working absolutely fine. For example, one classic example that people give is that even without the help of computers and all such fancy things, when the Eiffel Tower was built, it was through hand calculations, through very non-sophisticated theories, but the Eiffel Tower is still standing. All right. It's much older than the Howrah Bridge that we have in Kolkata, but it's still standing and standing very well. So the ultimate test of engineering is how well a structure is that is built is standing and working. Okay, of course, as we go along, we cannot be satisfied with these things. Okay, this is the most basic, simplest of experiments. Most basic and simplest of experiments is tensile testing. Okay, so for more innovative things, which we believe that the new generation of engineers will go on to do, we have to go for more sophisticated theories, more sophisticated ideas, which is what this course is a first step towards. Okay, so I hope you respect the age-old traditions as well as the need to go for deeper and more theoretical understandings of the things, okay, which we'll be studying later on. I hope that's it.
Yes, sir.
All
Thank
right.
you, sir.
Thank you. Let me stop the recording.